from the previous sessions, we have covered, we have done. From previous sessions, we have analyzed the capacitors. Then we discussed how we find the capacitance following a series of steps that we had to determine. For example, as a first step, we had to assign a Q. A second step, we had to determine an electric field. A third step, we needed to find the potential difference between the two components of the capacitor. And finally, the fourth step, it was determining C as Q divided by delta V. This was one approach. Another approach, it was using the energy which can be allocated in a capacitor. So this was one way. Another way was to find the energy, which is measured in joule. And this would be equal to 1/2 CV squared, at this part, we had to consider that the energy density, it is always proportional to, so the energy density, this would be equal to epsilon E squared, okay? So this is a unit which is joule per cube, and then once we determine this energy density, we will integrate this one over a contained volume, and afterwards we will have only to equal 1/2 CV squared, and this way we can still find the value of C. So we cover these aspects. So we expect you to know how to work with the energy, and then after we dealt with these topics, we talked about the boundary value problems. So we talked about the BVP, the boundary value problems, and in boundary value problems, we had a different approach how to determine the potential as a function of x. So here the question was the following: find the potential, and this would be Vx, which means that find the potential as a function of space parameter. This x can be a position vector of any point for any type of coordinate system. It could be spherical, cylindrical, or Cartesian. And in order to solve for the boundary value problem, we had to solve this equation. So the Laplacian of the potential, this would be equal to minus rho divided by epsilon 0. So this was the Poisson equation. Then we said that we can obtain the Laplacian equation in case this is Laplace equation, in case the free charge density is equal to 0. If the free charge density is equal to 0, the only thing that we would have to determine would be to write down the Laplacian in each respective coordinate system. And if you go over the examples we covered the previous session, you can understand a little more how the Laplacian equation can be written. The Laplacian Cartesian coordinate system, it is relatively easier. So this one can be formulated as, let me see how much of the board you can see. Let's see this way. Okay. So this would be the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z, times the potential. This would be equal to 0. So this is the Laplacian in the Cartesian coordinate system, which we can also read it this way: the second derivative with respect to x squared plus the second derivative with respect to y squared plus the second derivative with respect to z squared, v would be equal to 0. Regarding the Cartesian and the spherical coordinate system, the Laplacian operator, which is this operator here, you can directly read it or obtain it from a cheat sheet, because sometimes it could be complex. Now, regarding the Laplacian equation, we can assume, not assume, but we can consider, I believe you can all see this part of the board, Python nucleofluorescent Faraday, plus 400, so the Laplacian, this is equal to 0. We can consider initially the one-dimensional case. When we talk about the one-dimensional case, we're talking about the second derivative with respect to x of the potential. This would be equal to 0. Now, the solution of this second order derivative, it can be easily solved because we can integrate this expression twice. So this means that the second derivative with respect to x is 0. We integrate it once, and actually, I might erase this one afterwards. So we would have the integral of the d squared dx. This is the integral, right? And this is like this. And what we see here, actually, it might be better if we write this one like this: dv over dx multiplied by dx. So this is the second order derivative. We have to integrate over x, and in here we can say that this d over dx, they cancel out each other, and then the integral, it is the inverse function of the differential, so they cancel out each other, and we simply get dv. Actually, it might be also better if we cancel out this one and this one, so we cancel out this with this, and finally we get that this is equal to dv over dx. This is equal to a constant c, okay? Because the derivative of this constant c, it will be equal to 0. So we integrate once, we get this. We integrate once again, which is dv over dx, integrating over dx. This dx cancel out each other. This integral, it cancels out the differential operator. And from here, we see that this is equal to v is equal to c1x plus c2. What we may have seen these types of solution a lot. They might look like mx plus b, where m is the slope of the function and b is the intersection with the y-axis. Now, this type of solution, what we can see here is that what is essential in all the Laplacian equation. Okay, so let's not forget, this is Laplacian. All the solutions, what they do is that they are like a minimization function or an optimization function. And these types of optimizations, they are used a lot, even in areas where the solutions are not always analytical, where we need to integrate continuous functions. But these principles of the Laplacians, they also operate in a perfect way. Also, the data set is discrete. And I'm sure you're going to take courses such as signal systems, and right there, you're going to see, or you may see once again, how this Laplacian can be interpreted. And I find that as a very good opportunity to mention some important aspects of this one, which in principle, this is, if we have a Laplacian operation Laplacian operator in one dimension, what it means that we have to assign the potential at some point A and at some point B, and we need to kind of optimize. No, I think better is if we do it like this. We should do it like this. So let's assume that this is the potential and this is the x, and now we know that at some point 1, when x is equal to 1, the potential it is, let's say, 5 volts. At some point 4, the potential is equal to 1. Okay, so this is how we can. This is 1, 2, 3, 4, 2, 3, etc. So so we know what at 1 what is the potential, at 4 what is the potential. We need to find what is the potential when x is 2 and when x is 3. The solution here is going to be this line, okay? And because this Laplacian operator, as we said, it minimizes or optimizes or kind of finds the shortest path between these 2 points in the 2-dimensional space. Okay, this intuition is enough to provide a solution for much more complex cases. And what is also another important aspect is, so let's call this one kind of minimization function. And this is minimizing. You are finding the shortest path. That's good. Another interesting aspect, so this is one. Another important aspect is that we have no local minima or local maximum, which means that we can never get a solution. So let's say we know these 2 points. We need to find the value of potential in the intermediate values. We would never get a solution that is going to look like this. No, because this would be a local minima, this would be local maxima, local minima. So these problems, we have the minima and the maxima at the end points. Okay, so we can say that. Third aspect. So let's say, no, let's call it like this. The maxima and minima at end points, okay? So this one in red, this cancels out, we never get it, we just get the line in blue. It is also obvious that the solution is going to be a straight line, which is m is a slope. In this case, what is m in this case? We can try to identify this. M, it is going to be equal to delta y over delta x. What is delta y? It is 1 minus 5, 1 minus 5 over, so this is 1 minus 5 over 4 minus 1. 4 minus 1, because delta y, it is this distance, delta x is this distance, so we're talking about minus 4 over 3. So this is the slope. We have negative slope. You can use some very simple math to figure out where this is going to intersect with the y-axis, and we can use the similarity of triangles. We don't need to do this one in detail, but if it is something that we can do within 30 seconds, let's do it. Let's find what is the tangent of this angle here. So the tangent of this angle here, it is equal to this side, which is, what is this, 4, divided by this side, which is in this case 3. This would be equal to this side, which we don't know, okay, let's call this one y, divided by this side, which is equal to 4. So this means that the y, which is the intersection with the y-axis, not precisely, okay, but this is going to be 16 over 3. Y is not the intersection, y is this length, which means that this intersection is going to be 1 plus this, okay. So this means that y is equal to 16 over 3, and the terminology that we use here, the b intersection of y, it is going to be simply 16 over 3 plus 1, okay? Because 16 over 3 is this length scale. Good. So this is how these solutions will be. And another thing that we can mention here is that the solution of the Laplacian, in this case, it is always the average. So Vx, it's better if I write it like this, Vx is all can be written as 1 over 2 times the potential of x plus a plus the potential at x minus a. So this is like the averaging of a function, but when we find the average, we use 2 points. So if we're interested for a point in the middle, this point in the middle, it will be the average of 1 point to the right and 1 point to the left, add them up, divide by 2. And actually, what is also interesting, now that we see this problem here, I can say that this approach of the Laplacian, it can be used also when someone does image analysis, and we know that in image analysis, images are composed of, they are simply matrices, matrica, where we have some values which indicate the pixel intensity. And if you have a picture of yours, which would be 1000 by 1000, you can apply a Laplacian operator. And what the Laplacian operator will do to a pixel, it will find the average of this pixel, this, and this pixel, and it's going to annotate a new value. It's going to write a new value into here when we apply such a Laplacian operator. Okay. Then, so this is the case for one-dimensional, for two-dimensional. In two-dimensional case, we may assume that we know the potential at some x equal to a, x equal to b, and then y is equal to c, and also y is equal to d. So we know the potential precisely how it's going to change along this line, here and here. The question is this: Vxy is equal to what? Now, here the problem was minimization of the path connecting these 2 points. In this case, the problem, it can be interpreted as finding the shortest area which is going to join these lines. Okay. Again, we don't expect local minima or maxima, so we're not going to expect the potential to go something like this. No, because we may assume it this way. If we have how can I say, a small ball, and you drop it from one edge over the solution of the Laplacian equation, it will fly away. Okay, it will never leave here and follow this path in red, and the ball or the pebble, it will never stop here. Okay, if you drop a pebble, it will always go like this. So this will not happen. Similarly, solving a problem here, the potential along a specific direction, it will never observe a minima, a maxima, minimum, maxima. So it will always go linear, or we can call it like this. Let's say that we know the potential along this line, the potential along this line, and this piece of paper, which is going to represent the values of the potential, it's going to be a straight line, okay? Or it's never going to be something like this. You'll never see a solution like this, where this height at this very top, this will be the value of the potential. Apparently, the potential is dropping down to this value here, and it should never go increase like this again, but it would be rather something like this. So here it was minimization function, kind of shortest path length. Here, this will be, it will minimize the surface area which is going to join these points. Okay. Now, this is how the Laplacian equation is thought in 2D. Now, also in 3-dimensional, which is the problem that we like the most, with the x, y, z, find what it is given a set of points initially. Now, the visualization of the Laplacian equation, it will be slightly more challenging, but the way to think about it, it will be, maybe it's worth it, we should write it. Here, the potential of xy, this would be equal to 1 over 2 pi r integral of vdl. How do we read this? So we are still in 2-dimensional case. We read this one this way. Let's assume that we want to find the potential at some point here. The potential at some point here, it is going to be equal to the value of the potential integrating dl over this path divided by 2 pi r, okay? So we just integrate vdl along this path divided by 2 pi r, because this is the length scale. Now, the Laplacian operator in a discrete problem, which would be, as we said before, like an image, the value of this pixel here, which we do not know, this will be equal to the average of all of these pixels around. Okay, so this one, plus this one, We find the average of these, then we find the value of this pixel. So let's say that this is 17, 78, 100, 100, 105. And now, if we want to find the value of this pixel here, what we do is that we just do 100 plus 100 plus 105 plus 78 divided by 4. Okay, this is the discrete interpretation of the Laplacian operator onto a specific data set. This problem here, it is slightly more elegant, and then it's beautiful. It might be also a little more difficult, but this is how we think about this problem in this domain. And in the three-dimensional space, or in three-dimensional space, now let's assume that we have one point here, point P, which is point P, X, Y, Z. Now, the value of the potential right here, it is going to be the average of all the points which are allocated over a sphere. Imagine you go into three-dimensional space, you draw a sphere, and then you find the value of the potentials everywhere, you integrate it over the surface area, you divide by the surface area. So, but let me add this one. So the potential here at any point r, this will be 1 over 4 pi r squared. This is the surface area, integral of v dA. Okay. Now, how can we represent this one in a discrete manner? We know that in three-dimensional space, so an image, this is how it looks like, a picture that you take with your camera. But now, imagine now that you want to take an MRI, magnetic resonance imaging, and MRIs, they are three-dimensional pictures of the brain or of the heart, and they even call it, they are three-dimensional. If you include time, it would be four-dimensional, but we skip it for the moment. So imagine now that you have a picture of the brain, and now we don't have pixels, but we have voxels. They call it voxel. Anyway, it's good to visualize. So imagine now these voxels, they have some values which are here. We have also another layer to the front, here, here, then here, here, here. So you can construct a three-dimensional structure, and then the value of the pixel at the center, it is going to be equal to getting the value of this pixel here, plus this, plus this, plus this here, at the bottom again. So you find the neighboring voxels or pixels, you find the average, and an Laplacian operator applied into this MRI image is going to be the average of all the pixels around some surface area on the outside. Now, these Laplacian operators, they are very useful, at least in the applications where the data sets are discrete, because often the imaging specialists, they may need to improve the quality of the image. So if you want to get a good analysis of the image of the brain that you have obtained, you may need to apply these Laplacian operators. And you are very close to this area because all of these imaging techniques, they all operate with the waves. Okay, so you have a wave which interacts with matter, and you are going to learn more details of how a wave interacts with matter next semester. So you are very lucky that you take such a course. And so after the interaction, you understand how the wave changes. But then afterwards, once you have it in your hand, sometimes some of you that are taking this class might be lucky enough to work in medical imaging, which is an area which has a very high impact, because anything related to medical, it does have a high impact. So some days in the future, you might come up with these interesting operators, which are the implementation of the Laplacian operator in 2D or 3D. You have all the mathematical background how to solve these, because you have taken signal and systems in a more elegant way that few other departments take them. So you are among the few lucky ones. Now we'll start. This was the interpretation of the Laplacian operator in 1, 2, and 3 dimensions. Now let's want to talk about the boundary value problem in general.
Excuse me, we cannot see the...
Yes, thank you for letting me know. I have a problem with the camera, I cannot cover everything. Oh no, I did it, okay? But thank you for reminding me. I didn't want to include the region because there is a reflection from the lights, so you might even lose some information that might be written. But we fixed this. Now I will say a few words regarding the boundary value problem. This is the solution, let me call it this way, the second order differential. So they look like these. Before this class, I shared with you some references that you could go over and have a look of how we work with differential equations. But now, we'll try all together here to find what the solution of this problem is in less than 3 minutes, okay? So let's assume we have a differential equation that looks like this. And we have, personally, I always forget which one is which. So even if I were in an exam, that was what I was doing when I was a student. I would write this on a piece of paper. In 2 minutes, I would figure out what the solution of this differential equation should look like and what the solution of this other differential equation is going to look like, okay? Because, and these differential equations, we call these differential equation with constant coefficients. Constant coefficients. With constant coefficients is a differential equation which can be written like this. 3y plus 4y prime plus 5y, this is 0. These are all constant coefficients. Minus 2y double prime minus 3xy plus 5y, this is 0. This is this is a differential equation with constant coefficients. This is not. And the second equation, actually this is minus y, the second derivative of y with respect to x, minus 3x derivative of y with respect to x, plus 5y, this is 0. So this is just a cross, and it's not an x. So these two are the same equation, and we're just denoting that, or we're writing that y prime, it is equal to dy over dx. This notation, we might see this pretty often, the third derivative of y with respect to x. Now, these are no linear terms because we're multiplying the y with the second derivative of y. Here, we're multiplying the x with the first derivative of y. This makes no linear terms, and you know from linear algebra that anything linear is something which is always to the power 1, okay? As a small reminder, 3x plus 4y plus 4z, this is equal to 7. This is a linear equation. But 3xy minus 4z, this is equal to 5. This is linear. This is not linear because we have here the product of x and y. Then we come back here. These are differential equations with constant coefficients. Solutions, they always look like this. Okay? E is equal to, so if it is differential equation with constant coefficients, the solution, it looks like this. The question is this, what is m? Okay, then let's assume that the solution of this equation and this equation, it looks like this. Then the first derivative of y with respect to x, it is m e to the power mx. The second derivative of this function, it is m squared e to the power mx. So we are good so far, right? Assuming that the function looks like this, the rest should be like as follows. Then let's substitute here. The second derivative of y with respect to x, it is equal to m squared e to the power mx plus 4y. Y is e to the power mx. This is 0. Okay. So this differential equation is now written in a new form. Then the other differential equation here, this is going to be m squared e to the power mx minus 4 e to the power mx, this is 0. Now, e to the power mx, it's a function that looks like this. It intersects here the 1, it's always larger than 0, so we can easily divide both sides of the equation by this term. Okay? And it's never 0. If it was 0, the division would not be defined, but we are good. That means that this equation, we get here m squared plus 4, this is 0. And here we get that m squared minus 4, this is equal to 0. So a differential equation, using this substitution, it's now turned into a polynomial. And then here we find that m is equal to plus minus 2i, and here m is equal to plus minus 2. So here we have complex roots, here we have real roots. That means that maybe it's better if we write it like this. In here we have m1 is equal to 2i, m2 is equal to minus 2i. And here m1 is equal to 2, m2 is equal to minus 2. Then we have that the y, it is equal to e to the power 2ix plus e to the power minus 2ix. Here we get y, it's e to the power 2x plus e to the power minus 2x. Okay? Now, these equations here, since these are a complex number, this means that, in fact, this is going to be cosine 2x plus sine 2x. Okay? So, what we learn from here, in fact, differential equation of second order, it should have two linearly independent solutions, and this is one, this is the other. They are linearly independent because when we add these two together, we can get a 0 only when. So let's do it here. So the question is the following. A constant C1 e to the power 2x plus a constant C2 e to the power minus 2x equal to 0. When? If only for C1 equal to C2 is equal to 0, if it is 0 only in this case, here we imply that e to the power 2x and e to the power minus 2x, they are linearly independent functions. Okay? And now, let's see another, we don't have a third order differential equation, but we can say that if we have a seventh order differential equation, the solution, it should be a linear combination of 7 different linearly independent functions. But that's good. So we did these differential equations, we find the solution being this one. So this is an oscillatory solution. Oscillatory solution. This is an exponential solution. This is an exponential solution. So then we need to use this piece of information because the differential equations, they often, we are going to see that there will be either oscillatory functions or these. If there are oscillatory functions, we call these harmonic functions or time harmonic functions, and they are the easiest ones to work with. Now, that's good. So it doesn't take much time to go over, let me see, one. Okay, that's good. So it doesn't take much time to figure out actually which one it produces an oscillatory solution and which one produces exponential one. And one thing that we need to be careful here in this class that we are taking together is that we often will be asked to find a potential. So let's assume potential as a function of x, and this is x. Now, this is the 0 for sure, and depending on the charges, which can be given as a given initial value, when we solve such a problem, we have to consider the following. Let's assume that the problem that we're analyzing, it is defined from here up this way, okay? So let's say that our problem is defined here. Then, a solution that looks like this, y, this should be something like this, a constant e to the power 2x plus another constant c2, e to the power minus 2x. Now, imagine for a moment that the value of x is increasing very fast or is going to infinity. Then this term will diverge to infinity, which is something that we will not agree much, because we will be very lucky to have potentials that diverge to infinity. That means that we have a lot of power. Forget that. That means that once we are dealing like this, the constant C1 should be equal to 0. Okay? But similarly, if the problem that we're working on is defined only for negative values of x, which in this case would correspond to possibly an electromagnetic wave which is traveling along the minus x. Okay, so we do have these cases, and then if that's the case, the y would be equal to c3 e to the power 2x plus c4 e to the power minus 2x, and here, when x is negative, multiplied by minus 2, it will become positive. So that means that here, this one should be cancelled out. Or finally, we can say that this would be c3 e to the power 2x, and here we have y would be equal to c2 e to the power minus 2x. So we have to use our intuition into first figuring out whether the solution should be oscillatory or exponential form. Then afterwards, we have to figure out in which domain we are working on and how we can zero out certain terms in order not to obtain something unreasonable, which would be the case, as we mentioned. This would blow through the roof if we are working with positive x's. This will go through the roof if we are working with negative values. So always, whenever you find a solution, you immediately go and choose this option as a possible solution. Now, what we will see next is that, let's assume for a moment that the potential that we need to find is a function of x, y, z. And whenever this is a function of x, y, z, it is going to be very easy or relatively easy if the potential of x, y, z, if it is a separable function. Or separable expression. And being separable, you can assume being like this. So this potential, it could be represented as a function of x times a function of y times another function of z, okay? How would this look like? Well, an example, it could be the following. So example can be that the potential as a function of x, y, z can be equal to cosine 2x e to the power minus 2y times tangent z. Okay, so these are separable functions, and we often are going to assume that we have these types of solutions. Then this potential here, we can write it like this: potential x, y, z. This is equal to. Allow me to write, instead of f of x, just capital X as a function of space position x times y times z. So these are all separable functions, as I said. And the moment we want to write the, let's say, the Laplacian operator, let's look for a moment. So what would be the second derivative of the potential as a function of x here, given this example? The first derivative with respect to x, or let's say it like this, if we take the derivative with respect to x, here we do not see x explicitly in that expression. So this whole term, this will be a constant. So we can get this like this, e to the power minus 2y tangent z, and then we will take the second derivative of the cosine 2x, okay? So what is the second derivative of cosine 2x? Who can answer this? Second derivative with respect to x, this would be minus 4 cosine 2x, because cosine 2x, the first derivative, is minus sine 2x times 2, this is minus 1. We find once again the derivative, then we get the cosine 2x minus 4. So this another 2 comes out. So that's why we get this expression. Now, why we write this because now we need to find the second derivative or the Laplacian operator on this potential. And in this case, we can simply report the following, which would be, this would be the second derivative of this function times y times z plus the second derivative of y, but now the second derivative of y, it is with respect to y. This is z plus x, y, the second derivative of z with respect to z, okay? So this is, and let's assume this is the Laplacian equation, this will be equal to 0. Then we can divide this whole expression, or we can multiply it by 1 over x, y, z. Okay, so this is the first plus x so then this means that for the first term, the y and z, they will cancel out, and we will get the following. We will have the second derivative of x over the function of x. Then, from this term, we can cancel x and z. So this will be plus the second derivative of y with respect to y plus the second derivative of z over z. This is all equal to 0. Okay? So, in this case, as a small clarification, this is 1 over x times the second derivative of x with respect to x squared plus 1 over y times the second derivative of function of y with respect to y plus okay, so this would be the new way how we can represent the Laplacian equation for the potential V in case it is a separable function. But now, if this is a separable function, then what we can add here is that since this problem can be defined over a wide range of points, x, y, and z, you may imagine that the number of constraints onto this equation, it would be so large that it would make this problem unsolvable unless this is a constant C1, okay, this is another constant C2, and this is another constant C3. Because if this part, it is a function of Z, this will, actually we said this one, this will put too much constraints into the whole problem, and most probably it will make it unsolvable. But we are assuming now that this is C1, this is C2, and this is C3, and we have an equation where we have C1 plus C2 plus C3 is 0. So let's do C1 plus C2 plus C3 is equal to 0. Okay? But then, individually, we can also, let's try this one. Just for a moment. The first part here, this would be 1, let's say, 1 over the big function of x, second derivative of x, with respect to the little x, this is equal to C1. And then, we multiply both sides of the equation with a capital X, like this, and here, like this. These two cancel out, and we can finally say that let's do it here. Second derivative here, this is 2 with respect to dx squared, minus C1 x, this is 0. So now, it looks like the solution of this Laplacian operator for the potential, when it is a separable function, it comes down to this form, and this form, it's either this one or this, okay? So then, the solution of this problem, it is going to be either oscillatory, which is going to look like a sine cosine, or exponentially increasing and exponentially decreasing. Okay, so then finally we can say that this was 4. So then the solutions here is going to be something like this. This capital X, this is going to be e to the power square root of minus C1x. So it's going to look something like this. If we get a complex number out of this, this will become oscillatory. If we get a positive number, but we can always refer to these, then the solutions is going to look using exponential terms, but we're going to solve the examples, but for the moment, we can just, with the knowledge that we just covered in this session, we can say that x, the capital X, as a function of the space parameter x, it's going to be a constant C1 times cosine square root of C1x, square root of C1x, plus the cosine, sorry, plus the sine, or this would actually, plus C2 sine of square root of C1x. It's going to be either this or like this, C3 e to the power square root of C1x plus C4 e to the power square root of C1 x again. So it's going to be either this or this. Okay. Do you have any question for what we did so far?